What's going on, guys? Let's do this problem right here. The question is asking 3.2 mole of an ideal gas expands from a pressure of 5 atm to 1.4 atm at a constant temperature, right? Constant temperature of 170 127 degrees Celsius. Is work done by the gas or on the gas? That's first question. And the second question is asking how much energy was transferred by work and heat. So let's do the first question now. Is work done by the gas or on the gas? So whenever you see expands, that means it's done by the gas. If you see that's compressed, it's done to the gas. So here it's done by the gas. So the A part, the answer for A part is done by the gas. Done by the gas. Therefore, the answer work is going to be positive, right? So when we have done by the gas, that's going to be positive. When we have done to the gas, that's going to be negative. So that's the relationship. And let's go to the B part. The B part is asking how much energy was transferred by work and heat. So here, like this is an isothermic process because the constant temperature, right? Isothermic. So to find the work in isothermic process, we use this formula like W is equal to integral A to B P dV. So this is the one we use, and also P is equal to nRT because we use this one because as the pressure increases, the volume decreases, right? So according to the Boyle's law, but it doesn't decrease like straight line. So if we draw a PV diagram, it doesn't decrease like a straight line, it goes like a curve. So to find the area of this part, that's going to give us the work. So to find the area of the work, we can't use any direct like rectangle formula or anything, right? So that's why we use integral, and that's going to be A to B P dV. So instead of PV, we substitute this nRT over V. This comes from PV is equal to nRT, and we can substitute that one right here. A B nRT divided by V dV, that's going to be equal to, since dV, this is in terms of V, so we move the nRT to the front, so this is going to become nRT AB 1 over V dV, and that's going to give us nRT ln V, right? If you take in calculus, you know that 1 over V, if you integrate 1 over V, that's going to give us ln V. So this is the one we are going to use, ln V, and going from A to B. So here the A, B are final volume and initial volume, B is final volume and A is initial volume. So also, but if you notice here we have the pressure, we don't have the volume right here. So we have to find a relationship between volume and the pressure. So to do that, what we can do, so here the equation is basically nRT ln V final over V initial, right? Because you know that when we substitute this value, this is going to be ln B minus ln A. That is same as like when in the ln, when we subtract it means dividing. When we add that means multiplying. So that's how we derive this one. So now we have VF over VI. Now we have to convert this one into this equation, pressure equation. To do that, we can use the Boyle's law. So according to Boyle's law, PV is equal to P1 V1 is equal to P2 V2. So here what we can do, we have this, let's say initial is P0, so P0 V0 is equal to P final V final, right? So this is initial final. So to convert this one into pressure, what we can do is we can simply divide everything by P final over V0. So P final over V0, and if you do that, what's going to happen is here V0 cancels, and here PF cancels, and we have P0 over Pf is equal to Vf over V naught. And you can see the relationship between pressure and volume. And if you notice, this is the one we have right here. Initial, we can write V naught, right? So Vf over V naught, we can replace that one with P naught over Pf, because that is the one we want, because we don't have the initial volume or final volume, so we have to use the pressure to find the answer. So let's rewrite this formula in terms of pressure. So this is going to be nRT ln P naught over Pf. So this is going to be P naught over Pf. Now we can substitute all the values and find the final answer, because we have the moles provided, R we know that already, and temperature here is constant, but here we have to convert the temperature into Kelvin. If we have delta T, we don't have to do anything, because difference is going to be same for degrees Celsius and Kelvin, but here this is not a difference, right? This is just T. So we have to convert this one into Kelvin and multiply. And then we have the final pressure and initial pressure, so we can find the answer. So let's put all the values and see what we get. So we have the mole, that's 3.2 times R is going to be 8.3145 multiplied by the temperature. So we have to add 273 to this value. That's going to give us 400. So 400 Kelvin multiplied by ln P naught. So initial pressure, that is 5 atm, right? So 5 over 1.4. So this is good. If you plug all these value in calculator, you will get 13,548 joule, and that is the answer for the work. And we expect plus, as we discussed in the A part, it's done by the gas, so the work must be positive. So we got the positive answer. So that's the way it is, right? And then also they are asking for the heat. So here we know that this is the isothermic process. So delta U is going to be 0. Delta U is going to be equal to 0. Why? Because delta U is equal to nR delta T. And we know that change in temperature, there's no change in temperature. So initial minus final, that's going to be 0. So that makes everything 0. So delta U is equal to 0. Therefore, we know that heat equation is going to be Q is equal to W plus delta U. So since delta U is equal to 0, Q is going to be equal to W. Therefore the heat also going to be same as the work. Heat also equal to 13,548 joule. And that is the answer for the C part. Not C part, this is B part. Both of them are B part. And that's how we do these kind of problems. I hope you guys find this video helpful. Thanks for watching.